And I'd like to talk about testing uncertainty principle using currently available quantum computer platform. This is the kind of the curiosity-driven research about the quantum computer, which is slightly different from the goal-oriented research to make a fault-tolerant quantum computer. But now this is how to use this current quantum computer to useful way. And this use is obviously the quantum advantage, obvious, because this testing uncertainty principle cannot be done by the classical computer, because classical computer is a classical physical system. They cannot show any quantum law. So we start with what is Heisenberg uncertainty principle. Definition of the canonical conjugate observable is just the two observable Q and P which satisfied canonical commutation relation. Heisenberg's uncertainty principle is stated as follows. Canonically conjugate observables can only be measured and determined simultaneously with the characteristic inaccuracy represented by Heisenberg's inequality. Heisenberg's inequality is the inequality about inaccuracy of the measurement, which said that canonically conjugate observables Q and P can be measured simultaneously with their mean error or inaccuracy, epsilon Q and epsilon P, only if product of epsilon Q and epsilon P is larger than or equal to 1/2 of the H bar. And this is not proven by quantum mechanical rule. And however, in the same year, just after the Heisenberg paper was published in 1927, Kennard proposed and proved the following inequality for indeterminacy. The canonically conjugate observables Q and P can be prepared simultaneously with their standard deviation or indeterminacy, sigma Q and sigma P, only if the product of the sigma Q and sigma P is larger than or equal to 1/2 of H bar. And this statement is about the preparation of the state. In any state, we can prepare the standard deviation of the Q and P, the product for them, to be larger than or equal to 1/2 of H bar. But the standard deviation is not the quantity to indicate the inaccuracy of the measurement of Q and P done in simultaneously. And so the Heisenberg's uncertainty principle is about inaccuracy. In the German term, Ungenauigkeit of observable measurement, but not about indeterminacy. In German term, Unbestimmtheit of state preparation. So we have the two different relations. And Kennard's relation is, can be proved by using the Schwarz inequality in linear algebra. However, the Heisenberg's inequality could not prove it. And this is the original Heisenberg's paper in the starting part. There in the he summarized the content of this paper, and in German he stated clearly, it said that canonically conjugate quantities can only be determined simultaneously with a characteristic inaccuracy. And the characteristic inaccuracy was later derived by the thought experiment of gamma ray microscope experiment. So this relation is just the here epsilon. Oh, sorry. The relation is this epsilon q times epsilon p is larger than or equal to 1/2 h bar. This is this relation was derived by Heisenberg using the law of the Compton scattering. However, it's not general proof. And also, we are interested in not only simultaneous measurement, but also the measurement disturbance relation. Measurement disturbance equivalence principle says that any measurement of A with error epsilon A and disturbance eta B that is immediately followed by a precise measurement of B is considered as the joint measurement of A and B within joint error limit epsilon A and epsilon B is equal to eta B. So if you make a successive measurement of A and followed by the exact measurement of B, then those error for initial state is equal to the error of A and disturbance of B. And then the Heisenberg measurement disturbance uncertainty relation follows from the relation of the Heisenberg inequality for the simultaneous measurement. So this is the product of epsilon q and eta p is greater than or equal to 1/2 h bar. And this can be generally stated as follows. The measurement disturbance relation for arbitrary observables A and B is stated as the product of error of A and the disturbance of B is larger than or equal to 1/2 of the modulus of the expectation of the commutation relation for A and B. However, the Heisenberg's uncertainty principle is used to discuss the accuracy limit or sensitivity limit of the gravitational wave detection. There's a controversy over the standard quantum limit for gravitational wave detection. In 1980, Brzezinski, Thorne, Caves, and collaborators derived the standard quantum limit, abbreviated for SQL, to interferometer type gravitational wave detectors from Heisenberg's uncertainty principle, promoting resonator type approach. There are two competing proposals to detecting gravitational wave at that time. One is a resonator type approach, and the other type is interferometer type. And at that time, the resonator type is superior over the interferometer type because the resonator type does not have any theoretical limit of the sensitivity. But however, in that time, the interferometer type detector is believed to have the limit derived from the uncertainty principle. However, in 1983, UN claimed that such a limit can be broken by a contractive state measurement, which is some kind of the special measurement of the position he proposed. However, in 1985, Caves criticized UN's argument with a new proof of SQL and questioned the realizability of the contractive state measurement. However, in 1988, I showed that contractive state measurement can be realized, and indeed, the SQL is broken to settle the debate. In 1992, Thorne and co-workers obtained the NSF support for LIGO, Laser Interferometer Gravitational Wave Observatory Project. So after this time, the debate ceased, and NSF decided to support the interferometer type project to detect the gravitational wave. And then 2015, LIGO succeeded in detecting the gravitational wave. So the success of the gravitational wave detection had some origin in this kind of the debate about based on the Heisenberg uncertainty principle. And this debate is surveyed in the News and Views in Nature paper. And so we can summarize the uncertainty principle, Heisenberg's original formulation as follows. We say that there are two kinds. One is theorem can be proven from the basic axioms of quantum mechanics. The standard deviations of sigma q and sigma p of canonically conjugate observable q and p always satisfy sigma q, sigma p larger than or equal to 1/2 of h bar. However, another theorem, Heisenberg's uncertainty principle, canonically conjugate observable q and p can be measured simultaneously only with mean errors epsilon q, epsilon p, satisfying epsilon p, epsilon q is larger than or equal to 1/2 of h bar. This cannot be proved only by the standard postulate of the quantum mechanics, Q1 to Q3. It's the superposition principle and the Born formula and Schrödinger equation. We need also the approximate repeatability hypothesis, which assumes that after the measurement leaves the state in approximate eigenstate, but not necessarily this statement hold. For example, if you measure the photon number, after you measure the photon number, then photon cavity becomes not the same photon number as the measured value, or most of the time the photon number becomes 0 to be the vacuum after the photon counting. So there are many well-known measurements which does not satisfy this approximate repeatability hypothesis. So the Heisenberg's uncertainty principle cannot be proved generally. So I found the universally valid relation for the error of A and disturbance of B for arbitrary observable A and B as follows. Epsilon A times eta B plus epsilon A times sigma B plus sigma A times eta B is larger than or equal to 1/2 of the modulus of the expectation of the commutator of A and B. And this implies that if the error is 0, then the initial uncertainty of A times disturbance of B has this same lower bound. Or if the disturbance is 0, then the product of the error and the initial standard deviation of the B has the same lower bound. And also it can be possible epsilon A goes to 0 and eta B goes to 0 simultaneously if there are initial uncertainty of A and the initial uncertainty of B goes to infinite. So this can be manifest in the if you make a EPR state measurement of the position momentum in such a way. I skip some kind of the essential part of the measurement theory. Any measurement can be described by the interaction between S, the system, and probe P. And then after the interaction, the measurement result can be obtained by some meet observable in a probe, that is M. And after that process, the state of the S is prepared in some way. And in order to formulate Heisenberg's relation mathematically, we need a mathematical definition of the root mean square error in this way. And so we obtained the error disturbance relation for spin measurement in this way. And in this setting, we found that the Heisenberg original relation is violated in this special setting of the spin state for two spin component, X component, Y component. So we wanted to experimentally demonstrate this violation of the original Heisenberg relation. So experiment was carried out at the research reactor facility Trigger Mark II of the Vienna University of Technology by Yuji Hasegawa's group. So this is Atom Institute near the canal of the Vienna, and this is a research reactor in Atomic Institute. And the reactor hall is here, and we have the neutron from the reactor, and which is led by this route with the, this magnetic field. Then we have this sketch of the measurement system, but I don't have enough time to explain. And we obtain this curve for error and the disturbance. We have the detuning angle phi. The detuning angle phi is 0 if the measuring apparatus is the correct direction. However, if the correct direction is x, because we want to measure spin x component. However, the detuning angle changes from x direction to y direction. Then this is angle is plotted x-axis, and the error is plotted in y-axis. And we make a 10 instance of the measurement of the error and the disturbance for 10 different detuning angles. And then they plot it in this way. And this is obviously the different with the Heisenberg relation. Actually, so this curve violate Heisenberg relation because the product of the error and the disturbance is always lower than this is lower bound. Product of the error and the disturbance is always lower than the lower bound. However, there are some of the three product is always upper than lower bound. So this is my relation holds always, but however the Heisenberg relation always fails for these 10 instances of the preparation. And then a new relation shows the error and the disturbance. The admissible part of the error and disturbance is this part. However, the Heisenberg relation admissible part of the error and disturbance only the upper than this curve. And this experiment show that the error and the disturbance is plotted in this part. So the, it is not allowed by Heisenberg relation, have only allowed by my relations. And our experiment is published in this way, and the second experiment is given in Toronto's group by the measurement of the photon polarization. And also the Japanese group do their similar experiment. However, there are different methods. So we have the three kinds of the method of the detecting the error and disturbance. And those successful experiment is interpreted, this common interpretation of Heisenberg's uncertainty principle is proved false. Now, this is one way called the three-state method, and the other way, and this three-state method is used to demonstrate the relation in the neutron reactors. And also another way is weak measurement method. And this is used for detecting the, demonstrating the relation by using the photon polarization measurement. And also the experimentally used by a weak measurement method. However, in this photon measurement, there are very large noise here. Also, so we now demonstrate a new way of detecting the disturbance. We call this way the disturbance evaluation circuit, DEC. And our method is using this formula. And this formula shows that the two difference of the expectation value divided by 2 square of theta. And the limit theta goes to 0, it becomes disturbance of this measurement. So this is a good property because they need only the expectation value of the 2 states. So it's very suitable for using the error mitigation technique in a quantum computer. So we can use those currently available quantum computer, and those world record of the integer factorization is just there are 57. The Schwarz algorithm can be used only this number. So it is very much far away from the Schwarz algorithm for the RSA cryptography. However, those currently available quantum computer can be used to good demonstration of the Heisenberg relation. And the very nice point is that we have 10 years to find the experimentalists who wanted to do demonstrate this relation. However, now we don't need to wait for the experimentalists. We can do by ourselves using the quantum computer or quantum computer programming, Qiskit or Ticket. And so we have done the quantum circuit of using three-step methods and weak measurement method, and also new method, disturbance evaluation circuit in those ways. And we have the very good figure of merit using those three-state method, weak measurement method, and the new method, disturbance evaluation circuit. Those things we have with mitigation very low noise here. And now we have those plots, and there are some comparison between those three methods. And now the list of the experimental evaluation of the error and the disturbance, now we have those experiments. This is Vienna University technology using the reactor and the neutron measurement. And also those Toronto group, photon measurement, and those Japanese group by photon. And now we add new way, quantum computer, using quantum computer, and the new way, disturbance evaluation circuit. So we want to add further methods or detecting those error and the disturbance more accurately. And also we want to develop those techniques for other relations. And this is a very nice way to investigate the quantum measurement theory. Thank you very much.